So hi everyone. I'm going to start chapter 20 today. I updated the PowerPoint and I will upload the new PowerPoint to D2L later because this PowerPoint include a lot of details with a lot of examples. So maybe we cannot go over all the examples in this PowerPoint, but at least you can see the calculations. And I finished grading your lab. So I give some comments. Most of you did a very good job, but make sure your lab report you have to have a data table and you have to have your graph so that I know you actually collected the data and you actually process the data, okay? Because if you don't have your data table, any AI can write the lab report. So I want to make sure you did your work, you actually collect data and you actually connect the circuit, okay? So this is something I want to mention, but most of you have the right format for our lab report. So you just keep on doing that for our future report, okay? Unless I said something specific in the handout that you don't have to have that, just answer my questions. Otherwise, you still have to have the goal, theory, procedure, data, analysis, and summary. So this is the components for our lab report. So this is the lab. I'm going to stop there and we are going to start chapter 20 today. So chapter 20, this is something really connected to our daily life because it's electrical circuit. Electrical circuit applies to a lot of things in our daily life, like how um, any electronic device works in your household and how the connection how everything is connected to all the electronic devices to the household. So we can see the circuit connection and we can see how we build the circuit. You already had that in your lab. So this is a review of Ohm's law first, okay? So we have here in an electric circuit, an energy source and an energy consuming device are connected by conducting wires through which electric charges move. So here in this connection, usually we should have a energy source like this battery is the energy source and it's connected by wire and then to our device. Okay, so the wire goes the charges go through the wire, make a circuit so that our device can work. Okay, so here within a battery, so why battery can provide continuous power is because there is a chemical reaction happens and it transfers. So there's chemical reaction happening here, transfer positive electrons to the positive lead and negative electrons to the negative lead. And when the chemical reaction stopped, then your battery died, okay? So here, the maximum potential difference across the terminal is called electromotive force. So like here, the maximal, usually if it's a new battery, something like this is usually like 3 volts, but when the battery wears off, the EMF, the electromotive force will become smaller. Okay. So this is that, and it's the maximum potential difference. Okay. It's also what we call the voltage this battery provide. Now here, we did this in our lab yesterday, so you know what is current. Current is the motion. So see here, current is the motion of the charge, and it's by this equation, current will be equal to delta Q over delta T. So it's the charge. So you can count how many charges go through this surface in delta t in this amount of time. So use the charge divided by the time is the current. So it's the motion. So motion takes time and it's the motion of the charge. So delta Q over delta T. And the unit for current is ampere. Okay, so we use A to represent it. And we have two different type of current. We have DC current, like what the battery provided, and we also have alternating current. It's like what happened in our household. Okay, it's AC. Alternating current, usually our voltage, our power supply provide power like this. Okay, as a function of time, it changes as a function of time. So the current changes as a function of time, but for DC, then it's just a straight line. Okay, current will not change with time. Okay, now we have a very short calculation here. It's if we have a 3 volts battery of a pocket calculator, the current in the pocket calculator is 0.17 milliamp. So you are going to calculate in 1 hour of operation how much charge flows in the circuit. So it's very simple. You can do delta Q will be equal to current multiplied by time, which is given here. And then you can get 0.61 coulomb. Okay, the time for 1 hour is 3600 seconds, so it's 0.61. Using the equation, I will be equal to delta Q over delta T. And then we also have how much energy does the battery deliver to the calculator circuit. So energy, you can use here. It's what we talked about yesterday. Energy will be equal to the charge times the, this is not electric field, this is energy. The work done by the electric force, energy will be equal to charge times the potential difference. So Q times V. Q is 0.61 and V is 3 volts. So together you are going to get 1.8 joules. So this is the work done to the charge to move it, and you just use Q times V from yesterday. Okay. So usually, so here in reality, the positive electron cannot move. It's the electron that actually flows. But conventional current is the hypothetical flow of positive charges that would have the same effect in the circuit as the movement of negative charges that actually does occur. So in real life, because positive charges cannot move, only electrons can flow. So this is how the electron moves. But for conventional current, we usually go from positive to negative. So that's why we assume positive charges would flow, and then you can label your current this way. Okay, so go from the positive to the negative. So positive lead will have higher potential and negative lead have lower potential. So go from higher potential to lower potential. And then we have resistance. Okay, so you know most electronic device has resistance. So we have the Ohm's law. We have V go through the resistor. So here we have the light bulb here. It's when the current goes through the light bulb will light up because we have the current. Okay. So here, the resistance, we use letter R to represent it, and R equals to V over I, and we verify this in our lab yesterday. So this is Ohm's law. So you should be very familiar with Ohm's law after the lab yesterday. R equals to V over I, and the unit for R is ohm. Okay, so current is amp. Voltage is volts. So here we have voltage over current will be equal to the resistance. Okay. And also we have a resistor here. To the extent that a wire or an electric device offers resistance to electric flow is what we call a resistor. Okay. So resistor connected into a circuit, and build a circuit, we can have current run into the circuit. So here we also have a very short example here. It's the filament of a light bulb is a resistor in the form of a thin piece of wire. You can see here. The wire becomes hot enough to emit light because of the current in it. And the flashlight uses two 1.5 volts battery. So you have 1.5 here, you have 1.5 here. So the battery, you can do it like this, two batteries, okay? And then connect it like that. So if you have two batteries, our voltage will be equal to 1.5 times 2, which is 3 volts. And then we have 0.4 amp going into the circuit, so R will be equal to 3 over 0.4, which is 7.5 ohm, okay? So this is the resistance. The total here is 3 volts, okay? And the current is 0.4. Using Ohm's law, you can get the answer. So it's a very simple problem, application of Ohm's law. And then we have the resistance of how to calculate the resistance of a wire. So we have a wire, okay? For a wide range of material, the resistance of a piece of material with length L and the cross-sectional area A usually is like a wire. Okay, so this is A, this is L. So a resistance looks like this. How to calculate the total resistance for a material look like that? Then R is proportional to L and inversely proportional to A, but it's also proportional to a constant, which is what we call resistivity. Okay, so resistivity is in units of ohm meter, and we have different material have different resistivity. You can see copper or aluminum, they are conductors, so we have a very low resistivity. It gives very small resistance, okay? And then we have semiconductor, goes from 10 to the power of -5 to 10 to the power of +3. So those are what we call semiconductors. It's bigger than conductor, but it's smaller than insulator. So you guys remember I asked you to connect a coin to the circuit. So coin is made of, we don't have anything here, nickel. So it has a very similar property like copper, okay, 1.72 times 10 to the power of -8. It has a very small resistance. So that's why it has a very small resistivity. So it will give a very small resistance. When you connect the point to the power supply, R almost go to 0. So you will see the electrons goes really fast and maybe the circuit will be on fire because you are going to get a very big current. But also we have insulators like the rubber that you or paper you connect to the circuit. It will give you a very, because the resistivity is very big, so it will give you a very big resistance. So there will be no current in the circuit. So it's all depend on the different type of material. Okay, we have conductors provide small resistivity and a small resistance. We have insulators gives you very big resistivity and very big resistance. Okay? And then we have an example here. We can quickly go over this example. It's the instructions for an electric lawnmower suggest that a 20 gauge extension cord. So what is 20 gauge extension cord? It has distance, which is 35 meters. So this is the length of the wire, and but a thicker 16 gauge cord should be used for longer distance. So the cross-sectional area for 20 gauge wire is this. And the cross-sectional wire of a 16 gauge, the area is this. Actually, it should be meter square. The unit here is wrong. This is meter square because it's area. This is meter square. Okay, so this is the cross-sectional area. So this is our A, and this is our A. So determine the resistance of a 35 meter of 20 gauge copper wire. So copper, we should go here. This is 1.72 times 10 to the power of negative 8. So this is the rho. This is the L. And also 75 meter of 16. So L is 75. And then the area for the 16 gauge copper wire is 13 times 10 to the power of negative 7. Okay, and for this is part B. And part A, we will have length is 35. Cross-sectional area is 5.2 times 10 to the power of negative 7 meters squared. Okay, so with all the information given, take a look at A. A, this is how to calculate the resistance. So resistance will be equal to rho, which is this value, times L over A. Our L is here, our A is here, so you can get 1.2. And then we can take a look at part B and also put the rho here, length 75 here, and A here. So you can get 0.99. If you need, you can pause the video and then do the calculation by yourself to see if you can get the same answer or understand the application of this equation. Okay, so, but I'm going to continue. Okay, and here we can calculate the impedance of this seismography. So what is this? This is how to calculate the area. So area will be equal to volume divided by length. So that's why here R equals to rho. So calculate the resistance of this device. You can get R will be equal to L over A. So basically you can measure the pressure, the blood pressure. Okay, so L over A and the L is L and L become L squared and this is volume, okay? Because volume will be equal to area times length. So that's why you can get this rho times L squared over V. And we have the resistivity. You can see this table, this row for this table is only 20 degrees Celsius because rho will change with temperature. So here you can see our equation rho will be equal to rho 0 times 1 plus alpha t minus t0. So the resistance actually increases with temperature and it also decreases with temperature. So if you want to decrease the rho, what you do here is you put the device in a very cold temperature. So that's why when we have superconductor, but it's usually in a very cold temperature. We do not have room temperature superconductor. So that's why we have this equation here. Resistance also changes with temperature. Okay. And then we have the electrical power. So power will be equal to current times voltage. So this is how much energy is delivered in the unit time. Okay, so this is the power. Power equals to IV. And usually for a light bulb, suppose we have a light bulb, if the power is big, then it usually brighter. And if the power is smaller, and it's usually a little bit dimmer. Okay, so this is power. And for electrical power, power equals to, so here, when there is a current in a circuit as a result of voltage, the electrical power delivered to the circuit is power equals to current times voltage. And then we have power different, and unit for power is watts. And the power have different version of the equation. Power equals to I squared times R, and power also equals to V squared over R. Okay. And we have a calculation here of power. This is very easy, so I'm going to skip this example. You can just have current multiplied by voltage, and you can get the power. But when you watch the video, you should stop here for maybe a minute, try to do the problem and compare the answer here. Okay. So this is power, and for alternating current, so the usually the electric outlet in our household you see here is providing AC alternating current and AC voltage. Is because the AC generator, it actually rotates, so the direction of the power supply also changes. The AC generator is something that rotates in a circle. So once it rotates in a circle, it will provide alternating current. Okay, because we have to have limited space for our generator. We cannot let it move like forward in a straight line. It will take a lot of space, so we let it rotate. Once it rotates, the direction has to change. So here in an AC circuit, the charge flow reverse direction periodically. So that's why you can see our voltage changes with time, and this is a sine function, okay? And here, that's why it's a sine function. V will be equal to V0. This is our maximal voltage times sine 2 pi F times T. So F is the frequency. You know how to calculate the frequency. So from here to here is a period. And the frequency will be equal to 1 over the period. So you can get the frequency. And then we have in circuits that only contains resistance, the current reverse direction each time, and the polarity of the generator reverses. But if you only have resistance, current will be equal to this V0, so this voltage as a function of time divided by your R, so your current is also a sine function, and this is I0 is your V0 over R. See here, this guy will be equal to this. And then our average power, so power will be equal to current times voltage. So you have this little square here. And if you square the sine function, you are going to get a graph like that. And our average power, so you have minimal, you have maximal. Our average is in the middle, so it's 1/2 I0. So average is the dashed red line is 1/2 I0 V0. Okay, so that's why we have something called root mean squared voltage and root mean squared current. So it's the actual current that delivered to the circuit. So IRMS, so the actual root mean squared current will be equal to I0 over square root of 2, and VRMS will be equal to V0 over square root of 2. So this is the actual current and voltage delivered to the circuit. So this is that root mean squared, and then power is root mean. So for AC, VRMS, so RMS means root mean squared. So VRMS, so this is the Ohm's law in alternating current, and here this is the power in alternating current, and we have different equation for the power because we want the average power of over time. Okay, so that's why we have the bar here. We do not care about the minimal and the maximal, we care about the average. And then we have this equation here. It's a stereo receiver applies a peak voltage of 34 volts. So if you have peak voltage, that's your V0, it's 34. And then your VRMS should be equal to V0 over square root of 2, okay? Because we have it here. and then you are going to get 24 volts. And then we have, so after you get that, we go to the slides. 24 over the resistance, you can get the root mean squared current, and then power will be equal to I times V, which is 3 times 24, you are going to get 72. Okay. Okay. So here we have extension cords and a potential fire hazard. So during the winter, many people use portable electric space heater to keep warm. Sometimes, however, the heater must be located far from a 120 volts wall receptacle. So why is that? So an extension cord must be used. However, manufacturers often warn against using an extension cord. So you shouldn't use an extension cord, okay? If one must be used, they recommend a certain wire gauge or smaller. Why warning? And why are smaller gauge wires better than the large gauge wires? So it's trying to prevent it from being too hot, okay? Because we have the power here. Okay, so R will be equal to rho times L over A. So what do we have? If you have a bigger A, oh, we want it smaller. If you have a smaller A, you are going to have what? You are going to have a bigger R, right? So if you have a bigger resistance, what do we have? See here, because the power supply, the V here is a constant and usually it's about 110 volts. So if you want to have less power consumed in the wire, you want to have a bigger resistance. So that's why you should use a small area. Small area. Let me write the reasoning here. So small area R will be R bigger. Okay. Because we will have R equals to rho times L over A. So small area, bigger resistance, and the power will be equal to V squared over R. Okay. So less power. So less. Less hot. Less power. Yeah, less hot. Is that right to say it? So less power, we should consume smaller energy. So the wire will not become so hot. Okay. The reason, so sometimes if you charge your phone, you can feel like the connector is very hot. The reason is because the resistance in the connector also consumes power. And once it consumes power, it will become heat energy. So the more power it consumes, the hotter it will get. Okay. So this is power energy and AC, and we also have different. So see here, there are many circuits in which more than one device is connected to a voltage source. We have two different connections. This is the lab that you are going to do tomorrow. So we have series connection. The resistors are connected this way. So R1, R2 is like they are holding hands. So what we have here is the equivalent resistance, where Rs will be equal to R1 plus R2 plus R3. Because we are going to do a lab tomorrow, I'm going to quickly go over this and you can verify this tomorrow. If we connect two resistors together, if our Rs will be the summation of these two. And You can see here the current goes through the resistors, and it's the same for R1 and it's the same for R2. Okay, so that's why we have series wiring, means that the devices are connected in such a way that there is the same electric current through each material. Okay, so through each device. And RS, the equivalent, will be equal to R1 plus R2. And we have an example here. If you are connecting 12 volts to 6 ohm and 3 ohm, what you are going to get is 9 ohm. Okay, so very easy. And we have this example here. You can take a minute to try to do this, but it's just using 9 ohm, and you can use 12 divided by 9 to get the current. So 9 ohm, 12 divided by 9, and you can use the current to calculate the power. The reason we use current is the current is the same for these two resistors, and you can get your power together. For the circuit, it's this value plus this value. Okay, it's a very easy example, so I'm going to keep on going. And we have those personal electronic assistant. You can use the styrofoam to hit this writing pad. The device know when you actually where you hit the pad is because the resistance will be different. So you are creating a point of contact, and the total resistance connected to the crystal display will be different. And then we know which point you are actually in contact with. And then we have something else, is what we call the parallel wiring. So parallel wiring means that the devices are connected in such a way that the same voltage is applied across each device. So here we have the same voltage, okay? And the current is different. So see the current flow from here, and it split into two different branches, okay? So this is parallel wiring. So the wiring in our household is parallel wiring. So we have the power supply, and each electric outlet is a parallel to the power supply. So we can connect to TV, stereo, light bulb, and switch. And we have switch here. You can turn on and off the light bulb. Okay, but everything here is 120 volts. So the voltage connect to this light bulb is 120, to the TV is 120, and whatever other, maybe your washing machine is also 120. Okay. And we have, so this is more like, think about how current flow. So it's like if we have a water pump, you have one tube here and you have two tubes here. So I will be equal to I1 plus I2. And then if you have two tubes, it's like the area it's added, okay? So that's why for parallel connection, we have the equation like this, okay? So it's one, so if you have this, R1, R2, and maybe keep on going, R3. So if you have something like this, what we can do? It's 1 over, so the equivalent of this bunch will be, so I'm going to write this RP here, parallel. So the equivalent will be RP, 1 over RP will be equal to 1 over R1 plus 1 over R2, and keep on going, okay? So depend on how many devices you have, you can keep on writing this calculation. And then another example is we have a 4 ohm and 8 ohm resistor, and we can do parallel connection, and it becomes 2.67 ohm. We can take a look at the calculation here. 1 over Rp will be equal to 1 over 8 plus 1 over 4, and it's 3 over 8. Okay, 3 over 8, and you have to take the reciprocal. So 1 over Rp is 3 over 8, and Rp is 8 over 3. So 2.67, and you can get your current here. It's V over R. You can get your current. Okay, so this is the connection. Like this, it's parallel connection. Okay. When you watch the video, take some time to read this example. Okay, so it shows you the explanation of this graph and this circuit. And then we have a three-way light bulb and parallel wiring. Okay, within the bulb there are two separate filaments, so you have different brightness. So within there are two separate filaments. When one burns out, the bulb can produce only one level of illumination, but not the highest. So are the filament connected in series or in parallel? So it should be connected in parallel. Okay, so one didn't work, the other one could still work. And we have the brightest when both of the switch are connected. Okay. So it also asks you how can two filaments be used to produce three different illumination levels. So connect A, you have one level, connect B, you have one level, and connect both of them, you have the third level. So that's why it's very simple. Only two resistance is needed. And here, I want you to take some time to calculate this. So what is this problem? It's to find the equivalent resistance in the circuit. Okay, so find the resistance in the circuit equivalent. So you have this one, two are connected in series, and then these two together is connected to the 180 in parallel, and this whole thing was connected to the 110 in series. So how can we do that? It's we do the 220 and 250 together, we got 470, and 470 and 180 are connected. So this is in parallel. So you should get, for these two together, you should get one. Oh, I forget. If you have something like this in your homework or your exam, you can label this R1, R2, R3, and R4. So our R1, 2 together, so these two together is 470. And after that, you should get one R1, 2, 3 because you want these three together. Then it's 1 over R1, 2 plus 1 over R3. And then you are going to get R1, 2, 3. These three together, you are going to get it's 1 over 180 plus 1 over 470. So you are going to get R123, do it in your calculator, is 130 ohm. And then the 130 ohm was connected to the 110. So R1234, it's 130 plus 110, it's 240. Okay, so do it step by step so you can get the equivalent resistance, and also the current will be equal to V over R is 24 over 240, and you are going to get 0.1 ohm. Okay. And internal resistance. So we also have some internal resistance that was built in the circuit. So for our internal resistance, what we have is some energy will be consumed internally. So that's why our output V will be the, let's see. So here, if our EMF is 12, so let's go back, our output V will be the EMF minus current times the internal resistance, because there are some energy, there are some voltage consumed here. So this output voltage is not the same as this V here. So this V, we should call it EMF. Okay, so by the battery. So EMF minus the little IR is the output here. So that's why you can take a look at here. If our EMF is 12, let's take some time to look at this example. It's the terminal voltage of a battery. The car battery has an EMF, which is electromotive force of 12 volts, so it's here. And we have the internal resistance of battery is 0.01 ohm, so this is 0.01. And you are going to calculate what is the terminal voltage. So terminal voltage is from the two lead. When the current is 10 or 100, so if it's 10, what you should do is V terminal will be equal to EMF minus I times internal resistance. So it's 12 minus 10 times 0.01, and you are going to get, this is 0.1, 11.9 volts. Okay, so it's the same here. But if 10 is 100, then you should get 11 volts. Okay, so the bigger the internal resistance, the more energy consumed inside the battery. Okay, so sometimes the battery will get real hot because the internal resistance consumes some of the energy. And then we have the Kirchhoff's junction rule. Kirchhoff's junction rule is very interesting because it's the conservation of energy. So if you have 7 amps of the current, oh, I forget to tell you what is the junction. Junction is the intercept of all the current, okay, the intercept of all the wires. So here, this wire is connected to the junction, this wire is connected to the junction, and this wire is connected to the junction, okay? So if you have 7 amp going into the junction, you should have the same amount of current going out of the junction. So 7 will be equal to 5 plus 2. So yeah, 7 equals 5 plus 2. Yeah, that's all. So here, and also we have loop rule. So this is junction rule. And we have loop rule. So loop rule tells you if you have 12 here, okay, and then this 12 will be equal to 10 plus the 2 because this is the output and this is actually this is the input and this is the output 10 and 12. Okay, so the loop rule expresses conservation of energy in terms of the electric potential and state that for a closed circuit loop, the total of all potential rises is the same as the total of all potential drops. So for power supply, you have a rise, and then the current, you have a resistor or current. The current, you have a drop, okay? So junction rule tells you the sum of the magnitude of the current directed into a junction equals to the sum of the magnitude of the current directed out of the junction. And the loop rule is around any closed circuit loop, the sum of the potential drop equals to the sum of the potential rise. So this is Kirchhoff's rule. Kirchhoff's rule is based on the conservation of energy. Okay. And you can use Kirchhoff's rule to determine the current in the circuit. So how to do this problem? You can see here we have 24, we have 6, okay? So let me show you how to do that. See here, let's use loop rule. So 24 is the power supply. The whole thing should be equal to 0, okay? 0. See, rise will be equal to drop. Let's just start with 0. 24 is a rise, right? And then we have the 12 is a drop. So minus 12 times I, because V will be equal to IR. I is the current, 12 is the ohm. And then you have another rise. So we are going to determine this is a rise, okay? And then plus 6. And then we have another drop, minus 8 times I. Okay, so you can get this is 0 will be equal to 30 minus 20I, and then you can get your I is 1.5. Okay? Wait for, oh, this should be negative. Oh, because the current also go this way. Oh, this is a negative. Be very careful. It's a negative. And then you should have 18. This is 0.9. Okay, let's go back. This is a potential rise, so it's positive. So here we have current. Okay, current coming out of the, so current coming out from the power supply, we are going to call it a rise. Okay, and then here we have a rise. Oh, and current. Oh, this is current coming into the positive. So this guy is also a drop. Okay, if it's connected this way, then it's a rise. But this one here is a drop. Okay, so this is I. Because the current going like this is not coming out from the power supply, it's coming into the power supply. So this is a potential drop. Okay, and then yeah, so it's 0.9. I did it wrong because I thought it's a potential rise, but it's actually a potential drop. So not all power supply in the circuit will give you a potential rise, okay? So this is a 0.9 ohm. And then we have this problem here. Let's take a look at the reasoning strategy, okay? So how to use Kirchhoff's rule to do the problem. So first we are going to draw the circuit in each branch of the circuit and choose any direction. So if your choice is incorrect, the value obtained will be a negative number. So you just draw the current and choose any direction and mark each resistor with plus at one end and minus at the other end in a way that is consistent with the choice of your current direction in this step. So outside of battery, conventional current is always directed from higher potential to a lower potential. So positive, it's positive and negative. So if you have this, so you mark this positive, you mark this negative, okay? So applying the junction rule in the loop and the loop rule into the circuit, and you can get equations and you can solve for the variable. So we can follow this this reasoning strategy to do the problem. Okay, so let's see. How about this? If we have a connection look like this, it's 14 volts of the power supply here, and we have 12 volts of the power supply inside. Let's try to calculate the current. So this is the circuit. Let's try to calculate the current A, current B, and current AB, and current headlight, current H. So let's try to find IA, IB, and IH. So how to do that? Okay, so we can take a look at, so we can have this loop here, and we can have this loop here. So these are two different loops. Actually, we can have let's use this small loop and this big loop. Okay, I like big loop. So here, what we have is we have the 14. So look at the big loop, okay? Big loop. So we have the 14 volts, right? And then we have, this is a potential rise. And from here, positive to negative, you have a potential drop. So it's minus IA times 0.1, and then keep on going up. So we can have the big loop. So big, okay, big loop. And then here, this is IH. And then this is also a potential drop because it goes from positive to negative. So we have minus IH times 1.2. And then it will go back here. So go back here. So big loop, go back here. Nothing happens. So it's 0. And then we can take a look at our smaller loop. So go from here to here. So here to here is 12. It's a potential rise. And then this from positive negative to is a potential drop. So minus IB times 0.01. And then from here to here is another potential drop, minus IH times 1.2 will be equal to 0. And then we are going to have IH, the junction rule, because IH plus IB. So see here, let's take a look at this junction. You have two current going into the junction, and you have the IH coming out. So for here, IH will be equal to IA plus IB. Okay, so if you have a current positive to negative, so current positive to negative is potential drop. Okay, and go back negative to positive, it's potential rise. So this is a potential rise. If you have a current like this, negative to positive, potential rise. Positive to negative, we have potential drop. So IH will be equal to IA plus IB, and then you can solve the equation. We can do this equation 1 minus equation 2. So you can get 2, so 1 and 2. Yeah, you can use equation 1 minus equation 2, and then you can get IA. How to do this equation 1? Oh, we can get rid of the IH. So you can get 14 minus IA times 0.1, then minus 1.2 IA plus IB. So replace the IH with IA and IB equals to 0. And then 12 minus IB times 0.01 minus 1.2 IA plus IB will be equal to 0. So after you replace IH with IA and IB, you have two equation and two variable. So the next thing is 14 minus 1.3 IA and then minus 1.2 IB will go to 0, and then 12 minus 1.2 IA and then minus 1.21 IB will also be equal to 0. So now you have two equation and two variable, and then you can solve the problem. Let me find the answer. So then this is, we do this, so 2. And you have to do the next step. Oh, this is not that easy. You have to multiply by. So you can get IA in terms of IB. So IA will be equal to 14 minus 1.2 IB over 1.3, and then put your IA into this equation, and you can get an equation for IB. So let me do the calculation here. Twelve minus 1.2, 14 minus 1.2 IB over 1.3 minus 1.21 IB equals to 0. Then, oh, I have to do it here. And your IB, so 12. Your IB will be, what I got is negative 9 amp, and your IA will be equal to 19.1 amp, and then your IH will be equal to 10.1 amp. Okay, so this is the calculation. There are some algebra here that you guys have to go through, but this is the answer, and then you can do the calculations later, okay? Because the calculation is not that easy. But the physics here is get the three equations right, okay? So there's a big loop here, a small loop here, and we have the junction rule. Okay. And we also have on the measurement of volt and the current, which we already did in our lab. We have ammeter to measure the current, and we have a voltmeter to measure the voltage. So the ammeter should be connected in series with the circuit, and our voltmeter should be connected in parallel to the voltage. Okay, we did this in our lab, so you know how to do the connection. And the last thing for today is about the capacitor. Okay, so capacitor looks like this. Okay, but for parallel connection, capacitor, you are going to do the summation of them. So it's opposite of resistor. Okay, and in series, you are going to do this. So remember, it's different from resistors. And also, we can charge the capacitor. So if we have a current into the circuit, okay, so initially, if the charge here is 0, so as time goes by, the charge will start to accumulate here and reach its maximum, which is Q. So the charging process is something looks like this. Okay, Q will be equal to Q0 times 1 minus e to the power of negative t to RC. And this tau here is our time constant. Tau equals to RC. So R is the resistance in the circuit. And then charging the capacitor, we are going to get a graph look like this. So it do takes some time. So it's like charge the battery. You will see usually the go to the maximum. So the last 20% takes a longer time. Usually the first 20% takes shorter time because of the graph. The graph is exactly looks like this. So it's not a uniform charging. Our capacitor is the same. See this 20%, so from here to here, this little 20% takes this amount of time. But think about this little in the middle. This little maybe 50% also take this amount of time. You will see this amount of time, they are almost the same. So like if you charge your car, usually we charge to 80%. And this, like if you have an electric car, we charge to 80%. Usually it's the most effective way to charge. Okay, so it takes less time to charge. And then we also have discharging. So if the capacitor is fully charged, you want to discharge it. So you remove the power supply. So the current will start to go. So it's like a battery. The capacitor looks like a battery, and you have a discharging equation looks like this. So charging is this, discharging is this. Okay. And we have RC circuits. Yeah, there are a lot of application of capacitor in our daily life. We are going to do some charging and discharging experiment later, so you know how capacitor works. But for today, we are going to stop here. And also, this is the last one, is the physiological effect of current. If you have, let's see, if you have about 30 milliamp of current going through your body, then you are going to it will create physiological effect. You will have involuntary muscle movement. So you cannot control your muscle anymore if it's bigger than 30 milliamp. So that's why electrical grounding is very necessary. So the excess current can go to the ground. Okay. So this is the end of our lecture today. Yeah, so tomorrow we are going to go over the homework chapter. So this is the end of our first week's lecture. Okay, the end of our first week's content. So the exam 1 will cover chapter 18, 19, and 20. And tomorrow we are going to have a recitation, which we are going to go over the homework problem. And you are free to bring any homework to me tomorrow, or you can email me something that you don't know how to do. Email me the question number so I can go over those in the recitation. If you don't send me the number, I will just pick up the problem I think is difficult and go over with you, because we do not have the time to go over everything, every single problem that assigned. Okay. And tomorrow we also have a lab. I will try to make a video for the lab tomorrow, so you guys can get ready to write the lab report. So the lab is about series connection and a parallel connection. So I'm going to stop here for today. And thank you, Bethany, for coming. And I hope more people can come. Okay, bye bye. You too.